Hello everyone, welcome to our Design Day presentation. We are team 19038, also known as the Turbinators, and our project is the additively manufactured cooled turbine airflow and heat transfer rig, and our sponsor is Honeywell. For our team members, the industrial engineers is Cordy Charter, the team lead. I am Jessica Acevedo, the purchasing lead, and Michelle Manning. For our mechanical engineers, we have Austin Bradford, Jacqueline Higgs, and Augustine Watson. As a team, we are to deliver a compressed air test rig capable of measuring the pressure drop and temperature change through a rectangular duct emulating a turbine blade's cooling structures, which is referred to as a coupon. The issue to address is that the varying surface roughness of additively manufactured materials affects the properties of airflow. Additively manufactured parts have a varying surface roughness based upon the material used and the machine resolution. The development of the test rig will allow for analysis of the effects relating to surface roughness and potentially assist in the future development of additively manufactured turbine blades. The main objective of the design for the test rig is for it to be cost-effective and operational prototype that will accommodate different flow rates and varying coupon lengths.
To accomplish this task, we designed a compressed air test rig, which you see on the right. It's comprised of 5 major subsystems, including the test section and flow control apparatus or outlet. The flow control apparatus in blue is an apparatus that was lent to us by Honeywell. This allows us to manipulate the flow and even measure it. Taking a closer look at the test section, you can see some of the instrumentation we have mounted around our test coupon, which is in the light yellow. We have a differential gauge allowing us to measure the pressure drop and thermocouples too to help us to measure the temperature drop of the airflow. Taking an even closer look, we can see the plastic inserts allowing us to manipulate the flow. These are in orange and red. These allow us to converge the airflow to the size we needed for the test coupon in the yellow again. An even closer look reveals the pipe sleeve, which is made out of 304 stainless steel. This allows us to case the plastic inserts and withstand the pressures which are very high in our purposes. Notable features include the notches in the plastic inserts, which allow us to align the flow with the test section inlet.
Here we can see some of the prototype design iterations throughout the life of the project. Starting on the left, we have the nozzle and plenum integrated with the securing arms for a critical design review. On our next iteration for our technical data package, we moved to a pipe sleeve concept, but this design had steps and was completely cylindrical. The final design on the right removed the steps and added a flat surface for the securing spacers. Here's some of the critical instrumentation we have selected. On the left, we have the bare-end K-type thermocouples, which are chosen for their ability to read the changes in temperature rapidly. In the middle, we have our data acquisition system, which has 8 channels capable of digital and analog inputs, which allows for our thermocouples, pressure transmitter, and allows for more instrumentation to be added if needed. Finally, on the right, we have our most important instrument, which is our 0 to 15 PSIG differential pressure gauge, which will measure the pressure drop across the additively manufactured coupon. As Austin had discussed previously, our pipe sleeve and plastic insert concept, here we can see the design come to life. We were able to have the pipe sleeve manufactured and Honeywell generously printed the nozzle and plenum inserts. Some mock-up photos were taken to illustrate how the pipe sleeve and inserts interface with each other.
Now we'll briefly discuss some of the simulations that we did to reinforce our design. First, we have the total temperature plots, and these are for the test section, most notably the nozzle and 2 coupon hydraulic diameters into the coupon. One of the goals was to design for a temperature drop in the test section, and from the analysis, we can see that achieved. Next, we have the total pressure plots, and arguably these are the most important simulations of the 3 we're showing. We can see from the plot that once the flow reaches the structures, which is the rightmost portion where the pinhole features are, you get a significant pressure drop. Therefore, this validates that our design was constructed for a pressure drop. Lastly, we have our Mach number plots. Honeywell wanted the flow to remain subsonic inside the test section, and as can be seen, the Mach number remains well below 1.
Once the system is built, it must be tested. For the system level test plans, we first have to verify that the test rig is safe and seals with the desired operating procedure. Next, we have the flow control device, which will be tested to ensure it is achieving the right mass flow rate in choked flow conditions. As for the subsystem, we must check that the old digital pressure gauge provided by Honeywell is still accurate. The pressure transmitter also needs to be checked by comparing how the voltage input varies with the changing pressure. Lastly, we must check the accuracy of the thermocouples by checking that they accurately read freezing and boiling temperature. For the operating procedure, the first step is to insert the desired coupon and seal the test section to the desired specs. Next, it is important to verify that all the correct valves are open so that air flows through and out the system rather than pressurizing it. After the pressure source will be connected and the operator can begin flowing air. The operator will want to slowly and incrementally increase the pressure until it has reached desired operating conditions. For our purposes, that's 120 psig. Once at the appropriate pressure, one can alter the Reynolds number and mass flow rate by closing and opening the critical orifices. Once all desired flow conditions are met, testing and data collection can then begin. After testing is complete, the operator will slowly decrease the pressure back down to 0, and once air has stopped flowing, it is then safe to disconnect the pressure source and exchange coupons for another test.
For the results and data reduction, as of right now, our results are limited due to COVID-19. However, the test rig is mostly completed. The only needed factors are additional machining, certain components to be welded, and the completion of the subsystem testing. At the end of the project, Honeywell will receive completed instructions on how to complete the construction, how to test the test rig, and how to obtain data from it. Now, for objectives completed, as mentioned earlier, we had 4 main objectives. The objective of having an operational prototype and being able to adjust the flow rate is in progress due to inability to complete assembly and test. The test section is currently able to accommodate different coupons of varying lengths. Lastly, the budget is on track and should remain well below the $4,000 limit with the projected expenses. In conclusion, we had a few surprises, such as obtaining instrumentation without a manual. Then the COVID-19 situation worsened, and we had to plan and adapt to the situation to finalize the project. Next, we learned how to deal with different design concepts and requirements. We also learned how to do an in-depth research about the materials needed and different quotes on assembly and testing for a rig. Finally, we overcome problems such as learning new engineering concepts and software such as ANSYS, plus we overcome some team dynamics. Thank you to our sponsors at Honeywell, Dr. Curtis Timpson, Ben Camereth, and Mark Morris. We also want to thank our mentor, Dr. Greg Ogden, and the College of Engineering.